Good morning. I'm Mike Folk, and I'm delighted to be here to talk to you about the past, present, and future of HDF and the HDF group. I've divided the talk into three parts, which I call the early years, the middle years, and the future. And we'll start with the early years. In 1985, the National Center for Supercomputing Applications was founded by Larry Smarr and some colleagues at the University of Illinois. The purpose was to provide high-performance computing capabilities to the academic community. From the very beginning, it was clear that these high-performance computers would be generating enormous amounts of data, and one of the best ways to make sense of data was through visualization. They made the smart decision to bring in a staff of visualization experts that would help in creating applications to enable scientists to visualize their data. In the fall of 1987, a committee was formed called the Graphics Foundation Task Force, consisting of a number of the visualization experts as well as people from the Workstation Support Group, scientists, and others. I came across these meeting notes from a meeting on October 28th, 1987, in which they discuss the need to select a standard graphics file format. Some of the needs in the standard format would be that it should be an extensible data storage mechanism, it should be fast, it should have options for compression, and it should have clear compatibility for gridded data storage. They also gathered together some papers describing other formats, such as Utah's RLE format called SLATEC, Computer Graphics Metafiles, PICT, FITS, and others, and went off and did their homework, and a couple of weeks later came back and had another meeting, and these are the notes from that meeting. And in that meeting we can see that they decided to look at three different types of formats that they would develop: a simple raster image format, a simple geometry format, and a so-called all-encompassing hierarchical object-oriented format, or IHO. As they looked into what this all-encompassing hierarchical object-oriented level format should be able to do, they said it should be possible to store data in a method that hasn't been possible with other formats, should encompass every conceivable future type of data. If and when it works, the hope was that others would adopt it. It should at least make interesting research. It could be machine independent. And the hope was that all other data formats should be included as subsets of an IHO file format. IHO got people pretty excited, and they decided to run with that. Probably wisely, they decided to change the name from IHO to HDF, or Hierarchical Data Format. Here we have a picture of the first HDF specification written by Tim Krauskopf and Gage Paulson. Tim and Gage were the initial implementers of HDF. So Tim and Gage immediately set about implementing the very first version of HDF, a machine-independent file format that would enable scientists to share and visualize their data, move it around from machine to machine, would have the capabilities that we've just talked about. Version 1, as did all versions of the initial HDF, contained so-called primitive objects. Primitive objects were things like raster images, color lookup tables, the dimensions of a raster image, the aspect ratio that was to be used in displaying an image. The focus at that time was really on 8-bit raster images. So a primitive object consisted of a tag and a reference number, the tag telling the type of object, the reference being an instance of that object, and then an offset and length, the offset pointing to where in the file that object was stored, and the length, the actual length of that object. These were primitive objects in the sense that they didn't make up really the whole of a particular object that you might be interested in. So for example, with a raster, what you're interested in is not just the bytes that make up the image, but you want to know its dimension, an associated palette, and so forth. For that, something called sets were formed, and a set was simply a grouping of these primitive objects to form higher level objects. So a raster image set would consist of the image itself, the dimensions, the palette, perhaps compression information, and so forth. And then an API was created and a library written that would enable people to simply access a raster image, and it would get all of the information associated with that raster image. And tools were created to say, okay, display this raster image, and so forth. So the idea was that scientists shouldn't have to deal with this complexity underneath the hood, but the complexity was there so that an application could find out the information that it needed. And so that was version 1, and that was first released in the spring of 1988. I joined the HDF group shortly after that. I joined in July of 1988. And one of the first things I began to hear from the scientists, who were very happy with the tools and very happy with HDF, but they also wanted to be able to store not just 8-bit raster images, but higher dimensional data sets with floating point numbers in them. So we came up with the idea of a scientific data set. I think that name was one actually given by one of the scientists we were working with. And they also, the visualization folks, wanted to deal with 24-bit raster images. So sets were created for scientific data and 24-bit raster image, and that was version 2 of HDF, which was released early in 1989. Hot on the heels of version 2, we began to work on version 3. One of the things scientists wanted was the ability to subset, subsample, take small pieces of data sets instead of having to load the whole thing in at the same time. Not just data sets, but images as well. Another thing that happened was that the visualization people wanted to be able to easily represent triangular meshes and meshes with other types of components, because this was a very important part of what they did. And they asked us to create another kind of set called a V-set, or a vertex set, that would allow you to put, say, the vertices of all of the triangles in an image, and then the connectivity list of all of the triangles in the image, and then to put them in a set which would be grouped by something called a V group. The more we thought about that, the more we realized that this was a very general concept that didn't just apply to creating meshes, but all different kinds of data structures. So we sort of elevated the notion of a group to a level of a high-level object itself that scientists could actually manipulate and store things in, and so forth. And these sort of connectivity lists and these lists that would have the vertices, we looked at those and said, well, that's just a table of some sort. So we created a table structure. So V groups and V datas came out of that effort. And that was released in version 3 in 1990. And that actually, in a sense, was sort of the end of implementing new structures within HDF. The structures, any new structures that we implemented after that, were just kind of variations and refinements on that. And really the work that we did from then for the next 4 or 5 years focused on improving the library and improving the kinds of things the library could do. So for example, the ability to open several files at one time and work with several files simultaneously, similarly to open and work with several objects simultaneously. We also added new kinds of compression and that sort of thing. And all of that went into version 4, development of version 4 over a period of several years. Just as important as the library and the format, I would have to say, were the tools that were developed. And among them were a large number of command line tools. So, for example, show R8 would be a tool that you could feed an HDF file to, and it would display an image, a raster 8 image on your workstation. Show R24, show palette, and so forth. And there were a lot of these tools, and these turned out to be extremely important in the acceptance of HDF among developers and among users. Equally important, perhaps even more than that, especially outside of NCSA, was the development of visualization tools, visualization software, things that would actually display images and animation and data and let you get in and manipulate those. There were the big simulations at NCSA and the high-end visualizations that get worldwide attention, such as this thunderstorm simulation that we still see in the literature. There were desktop visualization tools for the Mac, for the PC, for Linux platforms that would allow people on their desktop to do some pretty nice visualization and manipulation of visual things. Not just raster images such as we see in the upper right hand corner, but also polygonal data. So PolyView was a really nice tool that was developed by the by the software development group, of which the HDF group was a part. And these were really important to the widespread adoption of HDF. But these tools weren't just developed within NCSA, and obviously there's a lot of visualization going on, not just with HDF, but with all sorts of data all over the world, and especially in the US. And here's an example of a tool that came, I believe, from JPL called LinkWinds, which stands for the linking of windows. And these tools recognized that a lot of scientific data was going into HDF, so whilst many of them had their own format, in fact most of them had their own format that was different from HDF, they also often implemented the capability of reading HDF files, and that was really very important to the widespread use and acceptance of HDF outside of NCSA. Another thing that happened, the first company, the first spin-off from NCSA happened in 1990 when Tim Krauskopf, I mentioned, one of the original founders of HDF and probably the most important person in the original development of HDF, and some colleagues from the university created a company called Spyglass, and the purpose of Spyglass was to commercialize, build commercial data visualization tools, and these tools were directly based on the tools that had been developed by the software development group at NCSA. And the success of Spyglass again brought HDF to the attention of a wide community of scientists and actually many people in non-scientific areas as well. Another thing that was happening in the early 90s was an increasing interest within the software development group, because this interest was coming from the scientific community, in remote access to data and remote collaboration. The idea that scientists in different locations could collaborate using the internet. The software development group developed several tools. The sort of capstone tool in this process was something called Collage. And the idea behind Collage was that you could have different scientists in different locations looking at visualizations of their scientific data, simultaneously sort of sharing the mouse and sharing the manipulation of the data. Another thing about collage was that because of the interest that we had in remote visualization, when we heard about this idea of the World Wide Web, which came along right around that time, we took a active interest in it. We had one of our folks, Dave Thompson, look into this World Wide Web and see what was going on with that. And Dave took a look at it, and he came back to us and he said, you know, this is a really amazing technology. And it's better than anything. It's better than Gopher and FTP and any of these other things that we've seen. And it has these things called browsers that allow you to sort of look at documents remotely, and it has a markup language called HTML that you write your documents in order for these browsers to work. But he says, you know, one of the problems with the browsers is they don't have any pictures. They don't have visualizations. And since visualizations was what we did, and we didn't know of any browser that did the same thing, we immediately started a project to create a visual browser. And that's result of that was Mosaic. Two of the folks in our group, Eric Bina, who was working on collage at the time, and Mark Andreessen, who was working on Polyview at the time, we took them off of those projects and had them work on this World Wide Web browser project. The result was Mosaic, which is, and I think people know Mosaic pretty well, and some people think of it as the first popular graphical browser, and one of the tools that really helped the World Wide Web and Internet to take off. What people may not realize is that in earlier versions of Mosaic, there was the capability not only of reading and interpreting and displaying HTML files, but of displaying HDF files. We did a little project in which a member of the HDF group, his name is Chris Hauk, created something called Browserama. And with Browserama, if Mosaic received an HDF file rather than an HTML file, it would convert a high-level view of that file to HTML and display it as an HTML document, and then it would allow people to sort of click on the objects in the file and drill down, and you could do subsetting and subsampling and visualizing of images and create plots and so forth. So that was a really nice little project that actually led to a number of interesting tools over time. Another thing that was going on in the early 90s that meant a huge amount to the HDF group was a couple of projects that were funded by the National Science Foundation. One of the things that we heard about almost from the very beginning, I know I arrived in the summer of 1988, and by the fall of 1988, scientists were mentioning to me this other format called NetCDF, that did many similar things to what HDF did. And it became clear that it was important for people to be able to work with, for certain scientists to be able to work with both NetCDF and HDF. So we wrote a proposal to National Science Foundation, which we called a NetCDF harmonization effort, and the idea was for the HDF library to be able to read and write NetCDF files, and fortunately that was funded. NetCDF read-write capabilities were built into the HDF library. It remains in the HDF library, and it's something that people rely on and use to this day. So that was a very interesting project, and it also was, I think, an indicator that the HDF group was very interested in collaborating with and partnering with other groups that were dealing with data. Another very important development was when NSF agreed to fund a proposal that we submitted under the NSF Software Capitalization Program, a very short-lived program. And the idea behind that program, which we're now seeing a resurgence of, was to take software that was produced in academic environments and to make it robust, to add user support, documentation, testing, make the software usable outside of the lab in which it was created. So we received funding from NSF for that. We hired Shiming Xu, who became our support, quality control, testing person, and that made a huge difference to HDF going forward. It meant, for instance, that the quality of HDF was sufficient that organizations outside of the academic community could begin to look to using HDF in their applications. And one of the most interesting applications in those early years was when the radiology lab at Massachusetts General Hospital chose HDF as the sort of back end for the storage of radiological images. And we worked with them, and over a period of probably a year to implement that system. And that was one of the really exciting early applications of HDF. Another one that I mustn't fail to mention is Phillips Petroleum, which was using HDF for seismic data, for storage and visualization of seismic data. And Phillips is important because they're the first company that actually provided any funding for the HDF project. They gave us $30,000, no strings attached, to help us develop HDF and strengthen it in whatever ways we thought were appropriate. Of course, they gave us some good ideas of things to work on. But that was a great group of people. And another interesting project was a European consortium called TRAPPIST, which consisted of a number of different organizations, very diverse, from nuclear power plant quality control to shipbuilding to aircraft design to medicine, that all did non-destructive testing, and they shared software and they worked together in that context. They had a format that was text-based, but just wasn't scaling in the way that it needed to, and they discovered HDF and adopted it as the standard format that would provide the interoperability that they needed as well as the scalability that they needed. This was a really interesting project from our perspective because it showed that HDF could be used well beyond academia, and it showed that people could take it seriously as a format. The biggest development in the early 90s in terms of users of HDF was NASA's Earth Observing System. The Earth Observing System has 3 primary satellites, each of which has several instruments, and then a number of other satellites make up the data gathering component of the Earth Observing System. Obviously, there are a number of different types of data, and that data really needs to be integrated, so the interoperability issues were really daunting for this project. The volume of data was going to be 3 terabytes per day, 1 terabyte per satellite per day coming out of this system, and the complexity obviously of the data that needed to be handled was also very challenging. Originally, NASA looked at 15 different formats. They spent about 4 years trying to determine which would be the best format to use for the system, and ultimately they chose HDF. I have to point out here that the NSF's role was very significant in the eventual adoption of HDF. The software capitalization project provided the quality and support that would be needed to make HDF a candidate for mission-critical operations of this nature. And the NetCDF harmonization was also key to interoperability, because a lot of the applications that would be using this were applications really that used NetCDF a great deal. So the ability to combine the NetCDF model and the HDF model in many cases was very important. So the message coming out of all this was that HDF really needed to support mission-critical applications with high quality and performance standards. One outcome of this new way of thinking about HDF was a need to look at how well it satisfied some of the requirements of these new types of applications. And there were clearly shortcomings of HDF. There were limits on the number of objects that could be stored in an HDF file. You couldn't have more than 20,000 objects. You couldn't have any object or file that was greater than 2 gigabytes in an HDF file. The raster, scientific data set, VData models were rather rigidly defined and not particularly applicable to some of the new applications that were occurring. I/O performance was beginning to be stressed, and as the code grew in complexity, there were definitely issues in our ability to maintain it and to evolve it in new ways. So several of us began to look for ways to address some of these issues. We spent some time originally trying to figure out how to evolve HDF itself to be able to address these various shortcomings. But because of the complexity of the code and because of the way that we had defined things, ultimately we decided it would really be better to start over with an entirely new format. One way, for example, of addressing the issues of code complexity and rigid dated models was to avoid creating a number of different objects such as raster images and data sets and tables and so forth. Instead, we decided that the new version would have one basic structure, a multidimensional array structure, where the elements of the array could be virtually any data type that you could define. This unified array structure, called a data set, combined with a rich collection of available data types, was very important to the success of the new version of HDF. With this new comprehensive structure, it would be possible to define all of the structures used in the original version of HDF. We see in this diagram how the table structure, the scientific data structure, the raster image structures all can derive from this structure. The table, for example, can be thought of as a one-dimensional array in which the data type can be as complex as you want it to be. We even had in mind originally that the grouping structure would be derived from this as well, as is shown here, but ultimately we decided against that and we created a separate grouping structure. So we shopped around our various ideas for the new version of HDF for some time, but unfortunately there were no takers for a while. Then came ASCI, the Accelerated Strategic Computing Initiative. This was an initiative that grew out of the Nuclear Test Ban Treaty of 1992, where it was agreed that there would be no more nuclear testing. So the issue was how to maintain the nuclear stockpile in the absence of testing, and the answer to that was very large simulations on much larger systems than existed at the time. So it would require new systems that would be orders of magnitude bigger and faster than systems that existed, say, in the mid-90s. The systems would become available by the end of the decade in the three primary defense labs of Livermore, Sandia, and Los Alamos. Applications would involve correspondingly several orders of magnitude more data. So data issues were an immediate concern coming out of this new initiative. And not just more data, but new parallel architectures would be there that would require new techniques for reading and writing data. A group was formed called the Data Models and Formats Group that consisted of membership from the 3 labs, and they looked at HDF as a possible format and invited us from NCSA to join the DMF group. The group got together first, I believe, in the fall of 1996 and began to look at the variety of different data issues that it had to face. One set of data issues simply involved describing the variety of different kinds of data and information that had to be accommodated in any new format and data management system. This diagram by Mark Miller of Lawrence Livermore National Labs, and we still work with Mark, illustrates the huge variety of different kinds of data and the challenges of being able to represent that data. A lot of the discussion focused on what kind of data format we should use and what sort of software we should have to develop in order to manage the data and deal with these data issues. Livermore itself was developing a format called AIO for Array I/O, and we said early on that HDF wasn't going to be able to meet the challenges that they have, but that we were thinking of a new version of HDF that really could address a lot of those challenges, and by working together we could hopefully address pretty much all of them. The result was we decided to implement this new version of HDF, which we originally called Big HDF. Ultimately we called it HDF-5. So the audience that we thought of for the new version of HDF would be really focused as generally as possible, but in particular applications facing big data challenges. Those applications we envisioned would be in every sector, every application sector, academia, government, and industry. We didn't want to be restricted to any particular kind of applications, so we had in mind that hundreds of different possible applications in every field, not just science and engineering, would be using HDF, and that we would have users virtually everywhere. As we see, the focus in developing HDF-5 was on scalable applications, dealing with complex data, data variety, parallel systems, and so forth. Basically technical issues. And this was all good, but there was an important missing part that many of us weren't considering, but actually that lay under the surface because a lot of people were making assumptions about this. To explain this, I'd like to take you back to my first visit to NASA in 1990 when I met Al Fleig, who was a member of the group that was looking for a format and other solutions to the data management issues for the Earth observing system. Al took me into a hallway and he pointed to racks and racks of tapes, and he says, "Mike, you see all these magnetic tapes here? There's a lot of tremendously valuable information on these tapes, but we don't know what it is, and we don't know how to get it off of there. Is there some way with HDF that we could put like a phone number or an address or some kind of information at the beginning of the file that would tell people what they needed to do in order to get that information off of the file?" That actually stuck with me. You couldn't do it in HDF, unfortunately, but when we developed HDF-5, we designed into it the ability to put what we call a user block at the beginning of an HDF-5 file that a user could put any kind of information that they wanted to. They could put a little bit of text in there that would have an address or a phone number or other information on how to get access to the file. A sort of related issue came up in probably 1997-98 time frame when I got a call from Ben Kobler, who said, Mike, you know, we're thinking here about how we're going to deal with long-term preservation of these petabytes of data that we're going to be putting into HDF as soon as the EOS system becomes operational. And we wonder what you guys are doing on your end in terms of long-term preservation. And my response to Ben was, well, we're not doing anything. That's not what HDF is about. You know, we're concerned with fast I/O and scalability and these various other things. Preservation, that's someone else's issue. And in fact, I said, HDF isn't really designed for long-term preservation. It's a rather complex format. We have to make it complex for a number of different reasons, and complexity doesn't lend itself to long-term preservation. Well, Ben said, well, I'm sorry, but we really are assuming that we're going to be storing data in HDF for a very long time, and we'd like you to think carefully about that. So now we're getting this message, not that explicit, but we can really tell it from people's behaviors, and that's that the various communities that are starting to use HDF are committing really critically important data to HDF for the long term, and they expect it to last.